So we've taken a look at different models that we can apply to studying DNA. The only thing that's missing is looking at DNA through an electrostatic perspective. So we're going to take a look at DNA as a giant charge. So that's the official name of that model, the giant charge model of DNA. And also some additional models, such as the capacitor model for a double-layered system. And the most important thing here is that we're not just looking at electrostatics, but by analyzing and looking at some equations that we can apply for these models, we'll be able to predict the folding of DNA with those histones to create nucleosomes. We'll also be able to take a look at DNA twisting, writhing, and linking. So when we take a look at DNA's charge or an electrostatic perspective on DNA, we're able to analyze and predict a lot of different behaviors that have been proven already from other studies. For the past few lectures, we took a look at DNA through various different models, but we never really touched on DNA in terms of electrostatics. So this entire section is dedicated to modeling DNA through various different electrostatic models. So we're going to assume DNA is just one giant charge. So the first thing we want to go through is an overview of this model. So the way we look at DNA when we're talking about an electrostatic model is that it's the most highly charged molecule in nature. Let's first draw a DNA ladder. So we have a DNA strand on one side and another DNA strand on the other side. Let's assume that you have some bases on each side. And those bases are going to be connected. So let's just assume we have one going here, so on and so forth, and continues. We're going to call each of these a phosphate with a charge of -E for elementary charge. And we also want to label this distance as approximately 3.4 angstrom. So with models, we've already discussed the fact that whenever we want to approach a good model, we use good parameters. We have these values here, -E and 3.4 angstrom, because they have been proven parameters that have been used before. So when we take a look at charge, it's going to be equal to -E over 1.7 angstrom. So let's try and figure out where this comes from, and we're going to go through a few slides to get there. Let's first take a look at the histone octamer. So we are starting our studies of DNA electrostatics, so starting with the histone octamer, let's first draw a diagram of what it looks like. So we're just going to assume this is the octamer. So remember, it was broken up into quadrants and then 4 pieces sliced in half. The histone octamer essentially has two copies of H4, H3, H2A, and H2B. So those are the 8 pieces that come together to create that octamer. The histone octamer itself has a positive charge, so it's a major player in DNA packing. So we're going to answer why in a bit. Let's first label this as 70 angstrom from here to here. .55 angstrom, and approximately it holds 220 elementary positive charges. So then let's go back to the question of why the histone octamer is such a major player in DNA packing. So this is very important because, as you've probably guessed, it attracts the negatively charged DNA and also because we want to neutralize both charges to create stability. So we're going to take a look at neutralization of charge in the next slide. So let's first go through what this means. The histone tails are positively charged while the DNA is negatively charged. So when the two come together, it makes sense that the charges are going to neutralize when you look at the entire molecule or complex. And that means there's going to be a competition between entropy and energy. So the way we want to think about it is by looking at a surface. So let's assume we have some sort of surface here. Probably draw this a little bit smaller. You're going to have cations here. And you have anions. Specifically here, you have a surface charge density of sigma naught. So let's call sigma naught a planar charge density. So depending on the way you look at this, if there are many negative charges for the DNA side of things, then for the histone side of things, we want some sort of C, where C is equal to the density of counter ions, which would be the cations to the anions. So it would be cations that help neutralize the anions from the DNA. So that's just a very general overview of what the neutralization of charge is and how we can model it. So there's going to be a certain number of anions that the DNA has, and then the histone octamer is going to provide just enough cations to help neutralize that charge. Next, we take a look at energy and potential equations. So we've kind of briefly talked about this through our studies of weak interactions. So let's take another look at this. We have an elementary charge separated by a distance r from another elementary charge. So the energy is going to be E squared over 4 pi epsilon naught epsilon r, which is equal to E squared over 4 pi epsilon r. So we simply want to combine this into the absolute permittivity. So absolute permittivity is equal to epsilon naught epsilon r. The next thing we want to do is try and figure out some sort of equation where we can model the potential or energy of the system. So we're going to define a few key variables and parameters. We have V being equal to the electric potential. We have epsilon r being equal to 80 for water, so that's the dielectric constant. And we have r being equal to Lb, which is the Bjerrum length. We also know from our previous studies that Lb is equal to E squared over 4 pi epsilon naught kBt, and from our assignments that was 7 angstrom in water at room temperature. So from all that, what we can do is calculate a potential equation. So it'd be a differential equation. So we have that being equal to negative E over epsilon and then we have sigma naught E to the power of negative E Vx over kBt. So that is a model that is commonly used to describe the potential of DNA as a giant charge. So looking at this, now that we know potential, we can move on to looking at not just one DNA strand, but 2 DNA strands. And when we take a look at 2 DNA strands, we are going to consider a capacitor model. So the double layer model is going to be between a diffusive layer and a backbone charge. So the idea really isn't with 2 DNA strands, for example. We kind of want to model it through some sort of space between the 2 strands. So let's take a look here. We have some sort of barrier or surface, and for DNA you have a whole bunch of negative charges on one side. This means that you're going to have counter ions on the other side. With some sort of separation distance x0. So in terms of the big picture that we're trying to accomplish, so this is let's call it the small picture. We now want to look at the big picture. Because the capacitor model for a double layer is essentially very useful when we're looking at DNA wrapping around a histone octamer. So this would just be DNA alone, so DNA strand alone. But with the big picture, we're looking at DNA wrapping around the histone. So that means we have our DNA going in like this, which I had in blue. Let's have the histone in purple. So with the histone, the big picture really involves us understanding that the histone is full of positive charges. And we also know that the DNA is highly negatively charged. So as the DNA wraps around the histone, so let's go this way. So going in this direction, it's going to maintain that negative charge all the way around because it's being neutralized by the positive charge on the histone. But there's also something else. There's this part, the small picture that we looked at before. And this really has to do with the counter ions that exist prior to the wrapping of DNA around the histone. These would be considered the small picture, and it would be counter ions acting on a specific area of the surface. So then we look back to the energy equations again. Because we're now looking at it as a capacitor model, we can say that E is equal to the total charge over 2C, where C is equal to epsilon A over X. So we'll have to define Q total as E sigma naught A and N being equal to sigma naught A. So that means a specific charge density across some sort of area, or a certain number of charges per area, multiplied by the charge. And when you combine all of it together, we get E being equal to E squared, or the electric field being equal to E squared A sigma naught squared X over 2 epsilon. So I'm not deriving these equations, but just presenting them. And from here, we can get the energy per n, where n is equal to the number of charges, and that's equal to E squared sigma naught X over 2 epsilon, which is equal to 2 pi kBt LB sigma naught X. So you might be wondering what A is. Let's go back one slide to that diagram again. We're just going to consider all this going around. All of this is A, the area of the surface. What the X is from that equation is actually this. That is X. Okay, so we've taken a look at one DNA helix, or just basically one strand of DNA, and we looked at the energy and potential equations for that. We then considered a capacitor model for a double layer when we're trying to wrap the DNA around the histone, and we also came up with these equations for the double layer model. We now want to look at DNA as a charged rod. So just remember, we're taking a look at different models for DNA electrostatically. We now look at a charged rod, and that means I have DNA as a charged rod. How can I simplify this? Well, we can create that barrier again that we had from before. Let's draw this a little bit closer. So you had all of these negative charges from DNA. There was some sort of distance, x naught, and there was also some sort of distance x, where all of the counter ions resided. We also found out that x naught is approximately equal to 1 over 2 pi LB sigma naught. And the key thing here is to note that the energy per counter ion is equal to kBt. So this is just a very, very simple diagram, and right now we're going to take a look at a few different cases to try and make some further predictions and analysis for the energy involved in these processes. So let's take a look at the two cases. We have throw this whole bunch of negative charges. Something like that. Okay, we're still looking at these two strands. So here, I have my energy per counter ion, and we found out that that was kBt. So that's going to be the same over here as well. We also have some sort of separation, H, between these two strands of DNA. And we're going to take a look at two cases. Case number 1. What happens if we have a really, really large separation distance? If we have a very large separation distance between the two strands or between the two different layers, what's going to happen is that there's going to be no interaction. Now, case number 2, we're going to say H is really small. It's a lot smaller than the separation distance between the two. The separation distance is going to be a lot smaller than the width of each of these, so this would be your x naught. So essentially, this means H approaches 0. So you're trying to stick these two layers really, really close together. And when that happens, we can assume that positive counter ions are released. So we're going to assume there are more positive charges than negative charges, so that the positive charges will be released. In other words, I don't know why this keeps. As your two strands get closer and closer together, so those are the two straight lines that I have here, your separation distance is very, very small. You have negative charges on one side, and you're going to have positive charges on the other side. But the assumption is that one side is going to be your histone and the other side is going to be your DNA strand. So we can assume that your histone has a bunch of positive charges, and you're going to wrap your DNA around it, and those negative charges are going to balance out. But also, in order for your DNA to be stable, your DNA is highly negatively charged and is going to attract a whole bunch of positive counter ions. So as your DNA wraps around your histone, a whole bunch of these excess positive counter ions are going to be released. So here, within this whole section, you have what's called a release of positive counterions. So what is the energy difference? In other words, what is delta E over this entity? It's equal to negative kBt. In other words, let's try and explain this conceptually. The two plates will attract each other. But another thing we're missing is some sort of parameter. So we're missing a parameter. And if you think about it, we just took a look at the two cases where there's a great separation distance, which means no interaction, and at really close separation distances, where the separation distance is essentially zero, you have the release of counterions. So even though there's a release of counterions, we've taken a look at the energy involved with that, but we haven't really looked at the entropic effect of releasing these counterions. So we're missing an entropic parameter, so we say that there will be an entropic effect associated with the release of counterions. So let's take a look at that in a lot more detail. So I've split this up into two slides because there's a little bit too much to talk about. So first of all, you have your negative charges lying down your DNA. And you also have here x naught, some kind of depth or width involved with the spread of positive ions. Now, the entropy per counterion can be written as the entropic contribution to the free energy. In other words, from our previous knowledge, we can say negative Ts is equal to negative kBt ln of W. So S is going to be equal to kBt times the ln of the concentration of counterions at the surface minus 1. And that's going to be per counterion per plate. And we're going to call this equation number 1. Now the next thing we want to take a look at is what happens in bulk. So essentially we took a look at the contribution at the surface. We now want to take a look at the contribution everywhere else. So that means we need a term not our definition, our expression for S. And that means S is equal to kBt ln of the concentration of bulk counterions minus 1 I'm going to call this number 2. And when we calculate 2 minus 1, we get delta S being equal to negative kBt ln of surface concentration divided by the bulk concentration. So we won't really be using this model in terms of calculations or whatnot because these are very broad models. But in terms of trying to figure out where the contributions are coming from, I'd say from here to here, we call this the entropic effect. But from here to here, we call that entire term the entropic contribution. So just for you to understand the two different terms, what is an entropic effect and what is entropic contribution. So now, to summarize everything, the two plates attract each other for H is a lot smaller than X naught. But this attraction is mainly entropic. In origin. Okay, so hopefully that makes sense. We're trying to say that even though there is an electrostatic attraction between the two plates, which is the histone and the DNA, when they get closer and closer together, they're going to release positive counterions, which is going to cause some form of electrostatic attraction. However, there's also a huge contribution from the entropic effect, and that has to do with the concentration of counterions in the surface versus the bulk. So we've kind of talked about a whole bunch of different things so far. We looked at just basically DNA by itself, and then what happens when we put DNA close to a histone. We end up having a capacitor model for two layers, or basically two systems. We took a look at different equations for the single and double layer model. and different cases where those layers get closer and closer together, and how we can calculate or be able to figure out the entropic effects of counter ions. Now we want to just take all of that knowledge and combine all of it to wrapping DNA around a histone. So we're back to the DNA histone, and let's quickly draw a diagram of what we expect to see happening. So I have my histone here in orange. And supposedly I have my DNA wrapping around it. So DNA coming in. And it's going to wrap around. Think like this. So DNA can wrap around histones like this. And when I'm taking a top view of this entire thing, oops, too far. Let's take a look at that top view. Oops. This is my histone of 70 angstrom. It's got a diameter of 70 angstrom, and it's going to I'm not sure what is happening. DNA is going to wrap around it. So obviously DNA is not going to be that thick, but we are drawing a representative diagram. So that is going to be the central axis of DNA, and it has a diameter of 90 angstrom as compared to the 70 angstrom for the diameter of the histone. So that's just a brief overview of how DNA actually wraps around the histone and what the measurements are. So the next thing we want to take a look at is how many turns of DNA is required for us to neutralize the charge on the histone. So we have this being remember there are approximately 220 positive charges on the histone, or histone octamer. How much is the total charge? On the histone, if we assume 1 elementary charge per positive charge, then that means we have a total of 220 E. Like that. So what this tells us is we need negative 220e on DNA in order to neutralize the total histone charge. So if we do the math, we have 220 times 1.7 angstrom is equal to 374 angstrom. So the number of turns is going to be equal to 374 angstrom divided by pi times 90 angstrom. So just remember from the previous diagram, so I'm going to go back to the previous diagram, this was 90 angstrom. So that's going to be the diameter of your central axis of DNA, and that means if we know the diameter, we're going to know the circumference, or 2 pi r, or 2d, so not 2d, 2 pi r, or pi times d, and then we'll be able to calculate how many turns are required, and that's approximately 1.4, which should be a fairly familiar number for the number of turns of DNA around a histone. So this is just an example of how a simple model can give us pretty powerful predictions. So the next few slides basically have to do with presenting more models for different types of energy, as well as free energy change for the models that we have presented, specifically our DNA histone complex. So when we take a look at the DNA histone, once again, our DNA is bending, which means we have bending energy. So we're just going to modify our previous equations. We have E bend being equal to kBt 1/2 LP for the persistence length, integral from 0 to the full length of 1 over r squared s ds. So then this portion, the integral portion, can be represented by 1 over r squared times 2 pi r times 1.4. So this is 1.4 turns. So try and think of where this term comes from and what this term is. Now, this term is going to be the total length of your entire strand. So then here, in order to get the total length, we would have 2 pi r, the circumference of your DNA central axis going around the histone, times 1.4 turns. So that means we can rewrite our equation as E bend is equal to kBt 1/2 LP times 1 over r squared 2 pi capital R times 1.4. And that's going to be equal to kBt 1/2 LP 2 pi over r times 1.4, and that's going to be approximately 50 kBt. And this means we can find the energy, well, we can find the change in energy and entropy. So that's the next step, being able to find equations to determine the change in entropic and entropy and energy. So let's take a look first at the energy change. The energy change is going to be presented by delta E is equal to negative kBt times 220 positive histone charges times 2, because there's 2 of them for the 2 layers. We have entropic change. And that entropic change is going to be delta negative Ts equals to negative kBt times 220 times 2 times the ln of the entropic effect, C surface, over the concentration of counterions in bulk. Okay, so let's try and visualize this a little bit. We have DNA being given as this. So we have all these negative charges here, and then we have a bunch of positive charges on the right. The histone is represented by another layer with a bunch of positive charges. And when it's by itself, it's going to seems like my colors have disappeared. Oh, no. It's going to be balanced by a whole bunch of negative charges on the outside. So that's when they're both standalone. When you add them together, though, so let's add DNA plus histone, you end up with your DNA histone complex. And that DNA histone complex is now going to have a bunch of positive charges on the inside, as we expected. And also a bunch of negative charges on the outside. So that would be our DNA histone complex. Next, we want to talk about the free energy change. So the change in free energy is given as 50 kBt minus kBt of 220 minus kBt of 220 times 2 of ln C surface of C bulk. And that is going to be equal to a negative number. So what does this mean? So we have a negative free energy change. This tells us that wrapping DNA around a histone can occur spontaneously. And that's absolutely crucial. And if DNA wraps around histones, and lowers energy, yet increases entropy, then the entire reaction is considered favorable. So from all of our models that we've just gone through, the most important thing is this. We found out through our models and by comparing the free energy and energy changes, we found out that the act of wrapping DNA around a histone is going to be favorable and spontaneous, which means it's going to happen naturally in real life. So we're pretty much done with looking at the DNA histone. The last thing I want to do is to go through a summary. So I'm just going to say we have a histone over here, and we're also going to have, just use this as DNA. Okay. Just make it thicker. So we know that there are 1.4 turns of DNA on the histone. In reality, it's actually closer to 1.75. So therefore, we're going to make a conclusion from this in a bit. Let's just first go through some of the positive and negative charges. We know that the DNA itself is going to have highly negatively charged DNA, and is going to attract a whole bunch of counter ions. So then with these counter ions, what's happening is, it's in green, and I'll explain it here. There will be a release of excess counter ions as the DNA strand joins the histone complex. So that means you have a bunch of these positive counter ions being released. As they're being replaced by the charges on the histone to help stabilize the DNA. So that means there's going to be the DNA is going to be highly negatively charged. There's going to be a high planar charge density of those counter ions, and they're going to get released as your DNA wraps around the histone. So one of the things is, now that we're back to the number of turns of DNA on the histone, using our measurements, we found out that it was 1.4, but in reality, it's 1.75. So what this tells us is that the DNA histone complex is what? If we think about it, if there's more turns of DNA on the histone, your histone still has 220 elementary charges that are positive, and from our calculations, we calculated that 1.4 turns of DNA would offer a counteracting negative 220 elementary charges of magnitude. So if I have 1.75 turns, it means that I have more DNA wrapping around the histone complex, which means that the entire complex would be more negatively charged. So in real life, the DNA histone complex is more negatively charged as a whole. And this effect or phenomena is called overcharging. So just a couple more slides. They basically have to do with DNA twisting and writhing. And this is just a very general overview of just another way to look at DNA. When I take a look at just DNA, and the simplest form is when there's no twist of the DNA, and also no writhing, which means there's no linking. Now we take a look at what happens if we have t equals 3. So what happens when we have t equals 3? What happens when we have t equals 2? Maybe t equals 1 and t equals 0 compared to different writhing factors. We have W equals 0, W equals 1, W equals 2, and W equals 3. So you probably noticed something with all 4 of these combinations. If I add up T and W, you get a total of 3. So linking is actually the summation of both twisting and writhing. But now we should probably figure out what all this twisting and writhing is about. Twist basically has to do with how squiggly those lines get. So basically how intertwined your DNA is just by itself within its strand. So if I have a twist of 3 and a writhing of 0, this basically means that I have very twisty DNA that looks like this, and there's 2 strands, so I gotta make sure I draw both of them. So that would be a twist of 3 and a writhe of 0. If I want to move forward with a twist of 2 and a writhe of 1, the key thing is this writhing number. It means that the entire DNA is twisting in upon itself. So that means I no longer have just some twist. I have a writhe of 1. So basically I've knotted it up once. So that would be that. If I have a twist of 1 and a writhe of 2, then there's less of the twist. So it's not as squiggly, but it means I've folded and I've created 2 nodes with my twist of DNA. So that means I have something along these lines. So that would be number 1 and number 2. And this would be number 1 for your writhe. And of course, if I have a twist of 0 and a writhe of 3, then technically this would be very smooth. And I would end up with something like this. With this being 1, 2, 3 writhes. And I've got to finish it off with just another layer of this. So then keep in mind for all of these, L is equal to 3. So we're kind of back to one of the first things we talked about here, which was DNA denaturation. Untwisting occurs when writhing is less than 0 becomes t is less than 0. So all this is saying is, oops, you have your writhing, and twisting. So it facilitates the untwisting for the transcription as RNA polymerase attaches and unwinds DNA. So I briefly just wanted to present this as a final method of modeling DNA, not really with electrostatics, but in this case it really has to do with the twisting and bending of DNA. So it kind of fits in with all of the folding of DNA around the histone octamer. So apart from just looking at DNA folding around the histone octamer, we can also consider DNA twisting and writhing upon itself. And when we take a look at transcription, which brings us back to denaturation, we can think about it as RNA polymerase trying to untwist and reduce the amount of twist and writhing to denature and unfold a DNA for transcription. So let's take a look at some of the most important topics that we've learned today. First, we took a look at DNA organization and structure. we were able to briefly understand what DNA is made of, its structure, interactions, and basically the process of how it folds around histones. The rest of the lecture, or the rest of the unit, was really about how we can model DNA in different ways. So we looked at many different ways of modeling it, as well as how to mathematically model them. We looked at the worm-like chain model. We looked at the elasticity of DNA. We looked at the zipper model for DNA denaturation, a specific case. We looked at the capacitor system for DNA as a giant charge. We looked at DNA histone electrostatics. And finally, we looked at how we can model the twisting, writhing, and linking of DNA. So those are just some of many different ways to analyze DNA. The more focused you get into these topics and these fields of studies, the more types of equations and models that will present themselves, and the more you can fine-tune these models for research purposes.